resources and energy efficiency. That will be followed up by a session on diversity, equity, and inclusion in the energy efficiency sector. Next, we'll have a session focused on how commercial PACE financing is helping property owners during the economic uncertainty. And then finally, we'll close out the day with a session examining power purchase agreements for energy efficiency projects, which we believe is a new way of being able to finance energy efficiency. This first session on distributed energy resources, energy efficiency, will be moderated by Brandon Renaud of sorry, my tongue is tied this morning. The City of Columbia Water and Light, a board member and a sponsor, and definitely a fantastic partner over the years, committed to innovation in energy. So Brandon, thank you so much for agreeing to moderate and this great panel today.
Thank you, Josh. And thanks to MEI for putting on this event. It's something we're at the City of Columbia happy to be a part of every year. It's so great to see the presentations that are put on. I want to welcome everyone to our first session this morning, distributed energy resources and energy efficiency. Our speakers will discuss today how the integration of distributed energy resources and energy efficiency into comprehensive energy solutions can unlock value beyond what either of those items can do on their own. I'm going to introduce our speakers today before handing off the camera and the time to them for their presentations. Today, we have Dan York. Dan York is a Senior Fellow of Utilities and Public Policy at the American Council for an Energy Efficiency Economy, better known as ACEEE. Dan is primarily engaged in utilities and local policy research and technical assistance. He has extensive experience in tracking and analyzing trends and emerging issues in utility sector energy efficiency programs. Dan has a bachelor's degree in mechanical engineering from the University of Minnesota, his Master of Science and PhD degrees from the University of Wisconsin-Madison. Both are in land resources with an emphasis in energy analysis and policy. He joined ACEEE in 2001. Welcome, Dan.
Very good. Thank you, Brandon. It's great to be on this panel, and I've spent a lot of time in person in Missouri over the years in Jeff City, working on some issues and watching the state develop its energy resources, especially on the energy efficiency side. So it's great to be visiting, even though it's virtual. So if you go to my first slide there.
Dan, I'm giving one second. I think we have Andre's presentation first. Let me introduce both, and then Andre's going to go first today. And we're going to have you go second. I apologize for any miscommunication there. That's on me. Our other presenter today is going to be Andre Bernstein. Andre is the group manager for the National Renewable Energy Laboratory, and he received his Bachelor of Science, Master of Science, and PhD degrees in electrical engineering from the Technion Israel Institute of Technology. Since October of 2016, he was a senior researcher and group manager with the National Renewable Energy Laboratory in Golden, Colorado. His research interests include the decision and control problems in complex environments and the related optimization and machine learning methods, with particular application to power and energy systems. Welcome to Andre, and we'll lead it off with Andre's presentation on real-time optimization and control of next-generation distributed infrastructure. Andre?
Oh, yeah. Thanks, Brandon, for this introduction. And I understand we have 15 minutes, right, for the presentation?
Correct.
Yep. Okay. So yeah, thanks a lot for inviting me for this very interesting event. So my presentation will be mostly focused on our project on real-time optimization control of next-generation distribution infrastructure, which was one of the pioneering projects in demonstrating how real-time coordination and control of distributed energy resources can help the grid to attain its goals, including grid services, energy efficiency, and resilience. So I guess we can go to, I should say, next slide here. So the focus of this project is on distribution feeders, microgrids, and campuses, communities, and community choice aggregation systems. So something that we can call soft microgrids. And if you go to the next slide. And the goal is to enable distributed and real-time operation, which is also network cognizant. And I will explain in a second what does it mean. And with the ultimate goal is to enable large-scale distributed energy resources, or DER coordination, to acknowledge customer and operator objectives. So if we go to the next slide. And the overall goal is to develop this real-time distributed and plug-and-play optimization platform that will coordinate and operate massive numbers of DERs, and with the three main goals: ensuring voltage and power quality, maximizing social welfare, and emulating virtual power plants. And next slide. So just quick overview. So this project was a collaboration of several institutes. The lead organization was NREL, National Renewable Energy Lab, but we had also Caltech, Southern California Edison, University of Minnesota, Harvard, and University of Colorado Boulder on the team. And next slide. I will give a bit of an overview of the technical approach. I know that I don't want to get into too much of technical details, but I wanted also to give a bit of a sense of how we achieve this coordination. So to illustrate this idea, consider this figure here, where on the left you have a distribution feeder that is connected on the right to some node in the transmission system. And these different circles here that you see on the left in the distribution feeder are different distributed energy resources, such as solar panels, batteries, or homes with those devices. In other words, aggregations of these different devices. This could also be, of course, residential buildings or commercial buildings or industrial buildings. And this distribution feeder is connected to some substation on the transmission system as shown in this picture. So next slide. So the overall goal of this project is illustrated here. So we have these three main objectives with respect to the different DERs and the system itself. So first of all, we would like to maximize customers and or utility aggregator objectives. So individual customer objectives in terms of their comfort, for example, in the houses, or energy efficiency. The second goal is to respect electrical limits within this feeder, such as, for example, voltage constraints, voltage bounds within the feeder. And the third main goal is illustrated here, the connection point between distribution feeder and the transmission system, where we would like to provide collectively from these DRs different grid services. In other words, implementing the so-called virtual power plant. So you can think of this point of connection, a point of common coupling of the feeder to the system, as a point at which a virtual power plant is connected, and we would like to provide services such as inertial response, primary frequency response, secondary frequency response, and following dispatch signals. We'll go to next slide. And the main focus of what I will show today will be focusing on basically the second part. Let me quickly tell you about the first part of inertial response and primary frequency response. Next slide. So the idea really is to take this feeder and create a power plant. And the idea is that this whole feeder responds to changes in frequency. And we can go to a couple of, maybe one more next slide. Yeah. Changes in frequency or changes in the rate of change of frequency proportionally, and these proportional coefficients D and M are prescribed by transmission system operator. But the goal is really how do you distribute these coefficients across different DRs to collectively emulate this response. And next slide. So this is what is shown here. Essentially, every DR responds as well to changes in frequency or rate of change of frequency with some coefficient, and collectively they respond with these prescribed coefficients D and M. Next slide. And I don't go into the details of this approach. I'm just wanted to give you a sense of this. So really, the idea is to use some optimization-based models and algorithms to compute these coefficients for each DR, ensuring given aggregate response. But one also important thing that we can incorporate in all of these models that I will show today is also fairness, equity, and economic indicators based on different locations of the DRs across the feeder. So the next slide. So the second part of services is more a slower response. So first is really the fast response, primary response, which happens on a millisecond or even maybe faster. The second is more on a second by second level, is basically secondary response, secondary frequency response, and in other words, following dispatch signals, maybe such as AGC signals. Next slide. And here the idea is to implement this distributed feedback system that I show on the left. And let me explain a bit about these blocks here, but maybe if we go to one more next slide, yeah, that will be easier. So the idea really here is that we have this distributed control system where at every house or at every aggregation of DRs, we have a local controller that computes set points to the devices or to the aggregation of devices based on local observations. And then there is a coordinator that has a global view of the system. It receives measurements from selected strategic locations in this feeder, measurements in terms of voltages, let's say, and the current flows. And it also receives measurements or measures the power flow at the connection point of this feeder to the transmission grid or sub-transmission grid, in other words, at the substation, let's say. And based on these measurements, the coordinator computes a price signal. So this is a virtual price. It just reflects some constraints within this feeder. For example, if the voltage is violated in some of these nodes, and it sends a price signal D to the individual controllers that take this into account when they compute their set points. And the goal is really shown here on the right, is really a threefold goal. First of all, tracking of signals at the point of connection, in other words, dispatching this virtual power plant, minimizing the cost of individual devices, and also enforcing limits such as voltage limits. And this approach, this distributed feedback-based approach, is very scalable. It allows you to scale to basically a limited number of devices, since you have a distributed computation at each house or at each aggregation of devices. So this is, yeah, next slide. So the second part, which I will not focus too much on this, is the trip, what we call a trip planner. So what I presented here was a real-time module that allows you to optimize and enforce limits in real time, but you also need to think of how to plan the system in the near few minutes or near few hours. And this is done using a second module that plans how you can plan the trajectory of this feeder in order to be able to provide services in the future. Okay, next slide. So what I want to focus in the last part of the presentation is really on what we did with this approach. We went from basic development, algorithms development, towards validation demonstration. And we had three stage validation and demonstration. First of all, we had what we call power, hardware in the loop. So what you see here, PHAL, it's the shortcut for power, hardware in the loop. So hardware in the loop validation is performed at the lab at NREL here. And the idea really is of this power of hardware in the loop, or PHAL, for those that don't know, is that you can have real devices such as solar inverters or batteries connected through co-simulation framework to a simulator of the network, and also connected to actual controllers, physical controllers. And you can emulate a real system through this system in a lab environment, but you have actually real devices you can control. So in this experiment, we had a real feeder from Southern California, Edison. The real feeder, by real feeder, I mean a model of that real feeder simulated in real-time simulator. And we had also hundreds of real devices in our lab that were connected to this feeder. At least 100 were actually physical, and hundreds were simulated or emulated. And we also had experiments at Southern California Edison with what we call controller hardware in the loop, which is CHAL, which doesn't include the actual devices, but it still has the controllers And we had 2 field deployments in Stone Age Farm microgrid in California and in the territory of the Holy Cross Energy Co-op here in Colorado. Next slide. So quickly, I will go over these parts. I don't know how much time I have left.
About 4 or 5 more minutes.
Yep. So let me go quickly here on the results. So yeah, I will not go too much deep on this, but yeah, we can go to the next slide. I guess this is a description of the feeder. We had at NREL, we also considered several DRs, as I mentioned. So what are those DRs? These are solar PV systems with different types of inverters and microinverters, batteries, electrical vehicle charging equipment. And overall, we had more than 51 penetration of renewables in this feeder. And as I mentioned, with over 100 controlled devices, actual devices. So the next slide. So here it gives you some idea of how this PHIL or CHIL setup looks like. You have in the middle the network simulator, which is a real-time power system simulator. On the left, you have the actual racks, we call them the actual devices connected to the simulator. We also have actual physical equipment like charging equipment that you see on down there. And actually each rack represents a house. So you have in this house, you have a solar panel, a battery, and an emulator of the load of the house, and so on and so forth. So next slide. Yeah, this is just the list of the devices. We can skip this one. So here, the next couple of slides will just show some of the results. Again, in the interest of time, I probably will skip on several of those slides, but it is just the idea of how this entire system operates. And here, for example, on this slide, you can see how this feeder that we had with actual devices was able to follow a given prescribed signal. You can see the dotted line is the band in which the power, the overall, the aggregate power of this feeder should be. And you can see how most of the time, using these coordination algorithms that I explained before, the feeder was able to be dispatched to this band of powers, aggregate powers, during the day. And in some areas, it was not able to follow this signal because basically there was not enough flexibility in the feeder. Yeah, next, you can go to next slide. Let me see, maybe we can skip a couple of those slides. Yeah, let's wait a bit here. So the next, as I mentioned, was experiment at Southern California Edison. That was not a real experiment and their real feeder, but it was in their laboratory. But we had the opportunity to scale this approach to the entire system that they have there. And yeah, maybe we can go to the next slide. So these are kind of the details of this system. This is, as you can see, we have a peak load of 50 megawatt, and we have also at least 50% renewable penetration. Yeah, let's go to the next slide. And here you can see different feeders. So if at NREL we had one feeder, here we had 7 feeders, maybe 5 feeders, and with these numbers of penetration and DR penetration and sizes. So yeah, we can skip to the next one. You can find these details, of course, in the slides that will be published. This is just a setup. Yeah, let's go to the next slide. And some results that also show how you can do 2 things, because I mentioned dispatch signals following, but also voltage regulation. Right. So this, for example, in the bottom here, we also show how we can use these coordination mechanisms to bring the voltages of these different feeders within prescribed bounds. In this particular case, because of high penetration of solar, the voltages were above the 5% limit. And using the coordinated mechanism, we not only optimized and improved the efficiency, but also brought the voltages to the limits, as we can show here on the right and the bottom. Next slide. So yeah, unfortunately, I don't have too much time, but there is also the other 2 demonstrations that we made in actual systems in Stone Age Farm. So Stone Age Farm is a winery in California. It's actually like a test bed to do different control algorithms. And we had there 20 assets to control. Similarly, solar systems and energy storage, electrolyzers, and gas turbine controllable loads. If you go to the next slide, Basically, this shows this microgrid. It's a system that is connected to the outside world, and we basically treated it as a feeder to control, similarly to what I described before. And next slide. And here it shows exactly similar performance, such as tracking of a given aggregate set point for that feeder. So dispatching on the upper portion. And let's go to the next slide. And this shows voltage regulation. So yeah, we can go to the next slide as well. Finally, just quick wrap up here. The final demonstration we had, and this is kind of also ongoing in ongoing other projects that we are pitching to DOE in future, is a very special experiment in Basalt Vista housing project. This is a project with Habitat for Humanity that was built for local workforce, for teachers and other people that support the tourism, let's say, in the area of Aspen in Colorado, which you can imagine is a very expensive area. And this specific neighborhood was built for people that cannot afford to buy $1 million worth houses. And that was also an opportunity to build from scratch and design from scratch all electric houses with rooftop solar, energy storage, electric vehicle charging, and smart appliances. Next slide. And the goal was to demonstrate how we can use these mechanisms, as I showed before, and help the distribution utility to control and coordinate DRs to provide value to the grid, as well as to satisfy the individual consumers. And yeah, we can go to the next slide. That was fully integrated with a given ADMS system. Again, if you need more details, I will be happy to answer. Next slide. And we had several, so this is just a snippet of results that shows how we could perform several tasks in terms of overall system performance, such as peak load management and optimization. By optimization here, we mean that we were trying to create really a net zero community with zero exchange of power, which was of course not always possible, but we tried to get to it as close as possible. So I think, yeah, let's go to the next slide. Yeah, we can skip. This is just zoom to those specific areas. Yeah, I think we can skip those slides, and let me see. I think we can, yeah, I will, I guess in the interest of time, I will stop here because I think we a bit out of time, but yeah, I will be happy to answer any questions.
Outstanding. Thank you, Andre.
Yep.
That's a lot of great information, and we do have some questions coming in, but what we'll do is save the questions for the end. At this point, we're going to hand it off to Dan York for his presentation on integrated energy efficiency and demand response programs. Take it away, Dan.
Great. Thank you, Andre, and thanks, Brandon. So go to the first slide here. I'm happy to be here again. Sorry for a little misstep earlier. Just got a lot of planning my own virtual conference. I swear my brain is a little bit scrambled these days, more than usual. So today we're talking about kind of the, Andre gave a really great look at the technical side of things, and I'm coming at it from the programmatic side. So we're looking at the benefits of integration, enabling technologies, research that ACEEE has done on just seeing what's out there in terms of, are we finding integrated programs? What are some of the barriers to those? And then kind of looking at the evolution of programs and into, this is a really great time because we've looked at that Basalt Vista development as application of grid interactive efficient buildings, or GEBs as they're known. So next one, please. So just in terms of benefits for integration, we kind of put 3 layers in here where the commonly realized benefits, and what I'm talking of integration, that's integrating demand response with energy efficiency, which is a subset of the whole universe of distributed energy resources, as DERs as they're known. So clearly customer bill savings are important, and those are realized through integrated programs. Increased participation, program satisfaction. It's just an easier for customers to sign on to just get a package of services that serve them rather than trying to figure out each individual program. And from a delivery standpoint, you can certainly lower the program administration and implementation costs if you just have one crew going out and doing multiple efforts to work with customers. And then the emerging benefits are a little bit stepping up to more the utility level. There's certainly improvements and benefits of increased resource adequacy and grid reliability, tackling grid congestion, and then this has to have a business case for it too. So looking at how we might incentivize the utilities, and then the last one there, just really stepping it way up to the wholesale market operations and the other services provided to the grid. So next one, please. So the enabling technologies, I think many of you or most of you are familiar with them, and it's the lowly thermostat reinvented by Nest and others, where we've got smart Wi-Fi enabled thermostats combined with advanced metering infrastructure. Direct load control switches is kind of old technology, but it still can work. And then tying those into mobile apps and marketplaces. Next one, please. And then commercial buildings, the types of technologies need building from the base up for smart building components, equipment with embedded controls that can communicate and interact with a central control system. And then that control system would be grid connected to tie this all together. Next one, please. And so, I've been at ACEEE 20 years, and one of my first projects was looking at the idea of integrating energy efficiency with demand response. And, that was research long ago, and many people recognized that that was a good idea back then. So, fast forward, and we did this research project just to see, well, what's exactly out there. So we started with a set of 52 of the largest electric utilities in the US as part of some other work we're doing. We reviewed their plans, had good information for 44 detailed utility plans, but we found only 5 programs at the highest degree of integration. 22 programs had some level of integration, and most of the integrated programs really are on the residential side. Those the smart thermostats and connected seem to be the gateway. All right, next one, please. So as we looked at these programs and just try to develop some kind of classification scheme, we kind of realized that we really saw 4 relatively distinct levels of integration. Level 1 was just recognizing that each type of program has benefits and capabilities for customers, but really not much, might inform a customer about something, but not really well integrated. And then you get to the next level where those programs actually promote each other, so that if you're getting an incentive for an energy efficient new air conditioner, you might get information about how you might tie that into a smart thermostat and get some demand response out of it. Level 3, administrative coordination, just that the programs have a common administrator. And then finally, a fully integrated program. Next one, please. And so here's some, we did find some examples, just the 3 here. AEP, Energy Management App for homeowners. PG&E had provided additional energy efficiency incentives for their DR, demand response customers. And then Southern Company has a pilot connected neighborhood, and where they're really incorporating a whole host of aggregated DERs. Next one, please. So AEP Ohio, and again, this was a couple years ago. I know things have changed in Ohio, but this program is really a smart home with demand response. And so it was a mobile app with the energy marketplace, with the energy bridge to inform customers, and then had connected equipment and devices. All right, next one, please. And BG&E had simultaneous enrollment for getting into their peak reward program, where you get a home energy checkup and some direct install, quick measures, And then you were also signed up for their peak rewards demand response program. So you got some energy efficiency off the bat, and then we're signed up for their demand response program. Next one, please. Then again, on the commercial industrial side, we didn't find that many integrated programs. I think there's a level of complexity and a whole host of other reasons why that's the case. I'm not going to read through these all these different program examples, but just showing that, that they're out there and in development. You know, ComEd, the Smart Buildings program seems, you know, that's a good start. Cross promotion, again, where you're trying to, like Eversource Massachusetts, facilitate enrollment in their energy efficiency and demand response. So they're promoting technologies that are eligible for both types of incentives and provide both benefits. Next one, please. Moving up, Excel Energy Colorado. They've got this energy management program that provides incentives both for peak demand and energy reductions. And then just jumping to the one program we found that we felt was fully integrated for Nevada Energy, their Power Shift Commercial Energy Services. So that's just a quick run through, and go to the next one, please. I'm trying to leave some time here for some questions here. So the barriers and challenges that we saw as we review these programs and talk to various people seems to be, starts with the internal organization of utilities, that traditionally the energy efficiency folks have been in one unit, and the people on demand response is a little bit more system operations. And so they were in a different place in the organization. So different goals, budgets, business cases, not always so well coordinated and communicating with each other. There's some regulatory hurdles. Now you've complicated the trying to figure out what's cost effective and what's within the domain of the utility programs. You need the rate structures. It doesn't make a lot of sense to have demand response if you have flat rates and not ability to get interval AMI readings of energy use and associated funding for those programs. And then just getting customers, they don't really care whether they're saving a kilowatt hour or reducing a kilowatt. So, but the program people behind the scenes are kind of looking for those. And then technologies still advances, but it's not as seamless as we'd like to think could be. All right, next one, please. So takeaways, again, we really found few fully integrated programs. Again, this was a year, 2 years old, but I don't think a lot has changed, especially given the last year we've had. That new technologies are creating opportunities for integration, that residential smart thermostat programs are most prevalent, and that you need organizational changes and supportive regulation to reduce those barriers. And those administrators, we certainly advocate integrating programs when those benefits outweigh those costs. Next one, please. And just a quick wrap up, here's what we see the next step for integration. And this gets back to GEBS, one of those sort of unfortunate acronyms that we've stuck with. But there's smart connected buildings, the grid connectivity and flexible loads clearly becoming important, as Andre well illustrated, the benefits and possibilities there. But we didn't really find any programs yet. Our ACEEE, we've got a GEBS working group of utilities interested in this, and it's almost all at the demonstration stage these days. Next one. And here's just a nice diagram of just showing the vision of what a GEB is all about, with renewables on site and storage and communicating smart technologies, grid connected, tied into the energy management system of buildings. So much more complicated universe for the customer. Next one, please. And we kind of see this as up here at the top, the kind of evolution of integrated programs is really leading to GEBS. And next one. And fundamental barrier that we find from talking to other utilities or talking to their customers is just figuring out what's the value to customers. So how much savings? Do we have time of use rates? Are there incentives in place? What are the costs for this additional equipment? How do they perform? Is this making my life more difficult? Is it too complex? Is it a hassle to get this all going? So far it seems like, customers are maybe rightly a little bit wary of making this big leap. Next one, please. I think this is about it. So from an industry perspective, we're talking utilities, the interoperability of energy management systems with grid controls and whatnot seems to be a barrier, as much as trying to get common platforms and things in place. Cybersecurity, clearly a common and very valid concern, and just having a workforce that can deal with the more complicated systems and building operators that can manage this. Next one, please. And that's going to wrap it up for me. Thank you for your attention, and we've got a couple of reports that go into much greater detail on all this work, and welcome inquiries as to our working group on GEBS, and turn it back over to Brandon.
Thank you, Dan. It's really interesting to see this topic both from the technical side, as Andre covered, and the programmatic side, as you covered. It's something that we hear a lot about in media, but to get really into the nuts and bolts of it and the application of it is really interesting to me. We have a couple of questions that have come in. Andre, I think the first one is for you. So from a practical perspective, how realistic is it to believe that consumers respond to the signals that you were mentioning, especially under normal conditions? Or is it that the signals are imposed by a network regulator?
Yeah, this is an excellent question. Ideally in my mathematical world, this is just imposed, and you have basically what I showed there. This is a distributed setting for a distributed controller, where you have this price signal that is sent to individual customers, and then at each customer's house there's a controller. For example, a smart thermostat, right? It receives this price signal, it takes it into account and adjusts the set points based on this price signal. For example, if you need to mitigate voltage violation somewhere, this smart thermostat will change its set point to accommodate this, right, automatically. So this is kind of in an ideal, world, technical world, but in practice, there is a human that comes there and overrides, right, for example, or does something like that. So that's actually a very interesting problem, and the system that we have is actually kind of robust to this thing. So it's just adapts to any human behavior. For example, if in some locations, in some houses, hopefully in a small percent of houses, people really override the settings, you just will use the others that basically it's because of this feedback system. There's like a feedback from the measurements. The system will just try more help from willing devices, let's say, right? Automatically, let's say, it's just by the virtue of how it is built. But from the policy perspective, regulatory, and how you actually incentivize people to participate in this kind of system, this is a separate question. So I guess, yeah, it's more maybe question to Dan and on this side of things. But in principle, when we analyze this kind of system, we also, at least we have a recent line of work where we really explicitly acknowledge the fact that there is a human in the loop, right? And of course, if there is a larger component of people that doesn't want to participate, this will not work, right? So you need to either incentivize somehow people. So maybe this cost that they have, because eventually this smart thermostat optimizes some cost locally. So that cost could be related to some incentives to people, and if they participate, they will get more money, and stuff like that. So but this is kind of a regular incentive idea.
All right, 30 seconds, Dan.
Okay.
One follow-up question for you. What and looking into your crystal ball, what does the evolution of grid integrated buildings look like, and where will they be in 10 years? 30 seconds, go.
I think they're not quite ready for prime time yet, but they're close. I think the key is, the big payoffs will be in the commercial buildings and whatnot, and just getting those systems to be reliable and easily implemented to get to the point of a more of a plug and play. Because if you have to redesign and work with all these different platforms and technologies, building owners already have a complicated enough lives to add another layer of complexity for their building operators. So it has to be, I think that's why the lesson from residential thermostats is that people put them up on their wall, and if they're good, they just work, and there's no big hassle involved.
Great. Dan, if you could just touch for one more minute on the commercial technology options. Could you touch back on that just for, I did say 30 seconds, but we have one more follow-up question. Just circle back to the commercial technology options just briefly.
Sure. Well, I don't have the slide up, but it's essentially you need all these, need smart components, whether it's your lighting controls, HVAC controls, and then a central building energy management system that's already working, not necessarily grid connected, but it's functioning as a central point. And then my understanding of GEBS is then you tie that in to the grid connection and that level of control too, so that you've got a building control system that can read signals from the grid and then tell the HVAC unit to make its adjustments, or lighting to adjust, or whatever it is, or you're getting power supplied from on-site renewables and you account for that. So it's all these different technologies that have to be a symphony playing on the same page.
Excellent, thank you. And Andre has also dropped a link into the chat if anyone wants to see some additional information on that. Thank you, Andre. I appreciate both of your time.